Good afternoon and welcome to the Nag Memorial Lecture. This is an annual feature in our institute. Typically around January every year since 2002 we have been having the Nag Memorial Lecture series actually. This was instituted, as many of you probably know, in 2002 in memory of late Professor Subhashish Nag of the Math Group of IMSC. And every year we invite an eminent mathematical scientist to the institute to give a series of lectures to our students and visitors. And one of these lectures is a public colloquium talk like today's, which is designated the Nag Memorial Lecture. And today's speaker is Professor Atish Dabholkar from ICTP, and I request my colleague Sujoy to introduce the speaker.
Thank you, Professor Arvind. So we're very happy to have Professor Dabholkar here from ICTP. He's currently the head of the High Energy Cosmology and the Astroparticle Physics section at the ICTP. He's also the director of the research at the Centre National de la Recherche Scientifique at Sorbonne Universities in LPTHE, France. He's a leading researcher in the field of string theory. He has made important and insightful contributions to further understanding of black holes and quantum gravity. And he's received numerous awards in recognition of his work in theoretical physics. So he was awarded the Bhatnagar Prize, one of the highest science honors in India. He was also awarded the Chaire d'Excellence of the Agence Nationale de la Recherche in France in 2007. I'm sorry for murdering the French language. He's also the recipient of the National Leadership Award from the President of India in 2008. So I'm very happy that he's here and I invite him to give the public lecture.
Okay, can you hear me? Okay. Well, I would like to start by thanking the Nag family for this and IMSC for this opportunity to lecture to this audience. It's a great honor for me to be here because, first of all, Chennai is the city of Ramanujan, and some of his remarkable works from almost a century ago have somehow found their way into the study of quantum black holes that I have been working on recently. And I, in fact, ended up writing a long paper with a number theorist, something which, with theorems in it, which is something a physicist normally doesn't do. And I have come to sort of appreciate the power and beauty of Ramanujan's mathematics, and that is, I think, equally matched by the power and beauty of the physics ideas that go into this. So I would like to convey to you this very interesting developments at the frontiers of theoretical physics having to do with quantum black holes. So this is, of course, an artist image of a black hole. This is perhaps a closer to how it might look like. Like there's a hole in space and then there are some stars that somehow deformed around it. This is what it actually would look like because it sucks in all the matter inside. So even though the black hole is like a hole, it's sucking in matter from the nearby stars and they get heated up and then they emit X-rays. This is how actually first black holes were discovered in our galaxy. So I understand that everybody, this is a broad audience, so I'm going to start at the very basics, assuming maybe college level mathematics or algebra basically. I will not use anything more than simple algebra. So one of the founding pillars of modern physics is the theory of relativity. It has two versions, special and general relativity, but I won't make a distinction. And one of the cornerstones of the theory of relativity is that the speed of light is the same whether you measure it on a platform or in a moving train. Now this is very strange if you think about it. For example, if you have a ball on the train, the speed of the ball at rest, the speed of the ball is 0. But if the train is moving at 100 kilometers, then from the platform it would look like the ball is zipping at 100 kilometers. Similarly, if the ball is moving in the opposite direction to the train at 100 kilometers, it would look like, so there you can imagine that velocity as seen from two different reference frames of a ball, cricket ball, is different. But apparently, according to Einstein, this is not true for the speed of light. And this leads to this very fundamental fact that it implies a relativity of time, that intervals of time measured on the train are different from the intervals of time measured on the platform, and that explains why the speed of light, those are called the Lorentz transformations, but you don't need to know that, but that's where the name comes from. It's the relativity of time that gives you the name of relativity. And time runs a little slower in the train, so this is the twin paradox you might have heard about, that your twin goes far away and so on. So there are all kinds of interesting consequences of that, and some of these are many of these are now, this has been now an extremely well established fact of physics, a very strange but extremely well established fact. And this also implies that speed of light is an ultimate speed limit. You can never exceed the speed of light, no matter. So even if you go, suppose the speed of light is 300 kilometers per second. Now you might think you get into a train which is moving in the opposite direction, then the speed of light will go up, but that doesn't happen. And this has two dramatic implications. One is gravity waves and the other is black holes. So let me explain to you gravity waves. So let me ask you a question to this audience. If the sun disappears right now, instantaneously, when will Earth come to know about it? Yeah. Whereas everybody here is, of course, a post-relativity person, but if you were at the time of Newton, you would have said instantaneously. Because if you remember from your high school, Newton's law is inverse square law proportional to the mass of the sun times mass of the earth. So if you put the mass of the sun to 0, gravity will just disappear instantaneously. And this actually bothered Newton a lot. It's actually, there is a remarkable passage from Newton's. He said that this cannot be true. But on the other hand, his law seemed to work very well in describing planetary motion. But he was really bothered by this fact. And the full understanding of it actually had to wait 300 centuries. And according to Einstein, it will take 8 minutes later, because that's the amount of time light takes. So since light is the ultimate speed limit, force of gravity should also travel at the speed of light. And that is what is called a gravity wave. So this was one of the predictions of Einstein's general theory of relativity. And he sort of gave up on it because he thought that it's never going to be possible to measure it. But as we will see, very recently you must have heard about the LIGO experiment. There is a very remarkable experiment in which such gravity waves have been detected, and with very detailed understanding of how those gravity waves are emitted. So next consequence of the ultimate speed limit are black holes. So again, all of you know a bit about escape velocity, right? So if you throw a stone like that, it will go and fall somewhere, right? It won't continue. But if you really throw it fast enough, it will go further. Now if you throw it at sufficiently high velocity, that's called the escape velocity, orbital velocity, then that's how the satellites move, right? It will keep on going around the Earth. And if you throw it slightly faster than the escape velocity, then it will just escape. But that raises the question, you know that the force of gravity actually increases if you go to Jupiter, because if you make the planet denser, either bigger or smaller, bigger in mass or smaller in radius, then the force of gravity goes up. So therefore, if you consider a sufficiently big planet or a sufficiently big star, the escape velocity would have to be the speed of light. But once again, according to Einstein's famous principle, nothing can travel faster than the speed of light. So what should happen? So what if the escape velocity equals the speed of light? Then even light won't be able to escape the pull of gravity. It's like light is like you can think of it as a photon or a particle, and the force of gravity is so strong that even light cannot escape. This is a very heuristic way of talking about black holes, but there is a more involved theory and solving Einstein's equations. But the basic picture is that there should be a kind of a black hole. And one of the defining properties of a black hole, so this is again artist's impression of a black hole. So this certainly looks like a black hole. So it's a black hole sitting here. So here it could be just a sphere, black sphere, and this surface is called the event horizon. And this surface has a very peculiar property. It's like a one-way surface that you can cross it one way, you can fall inside it, but you cannot come out of it. And that happens because it's actually, even though this surface looks stationary, that is fixed at some place independent of time, is actually moving at the speed of light. And once again, since nothing can travel faster than the speed of light, once you fall inside, you cannot catch up. So this is once again a very peculiar property of black hole space-time. And once you fall inside, you will be sort of, there is a singularity, but not over there. So what happens in the black hole is that, so normally you would think that if you fall inside a star, the center of the star is over there, you're still falling. But the singularity of the black hole is actually goes in your future. So the time and space sort of change their role a little bit. And you will meet a singularity in the future and you will sort of get pulled into kind of spaghetti. So it's a very bad way to die. Now, the history of black holes is very fascinating, and there are some nice discussion, I think, in the book of Kip Thorne on black holes, which I would encourage you to look at it. I mean, it shows that how ideas in theoretical physics evolve in a very, we sort of, once we read it in a textbook, is given to us, okay, there is an equation, there is a solution, and there is a black hole. There was a long intellectual battle about whether to really believe in black holes, whether they exist or not. Are they just some fictitious things? Are they superstitions or whatever? And Chandrasekhar, the great Indian astrophysicist, concluded by studying some electron gas and so on, that a star slightly bigger than our sun, once it runs out of the nuclear fuel, so why doesn't our sun collapse? See, our sun has a kind of nuclear explosions happening on it all the time, right? It is a fusion reactor. So even though gravity is trying to pull you in, the hot gas is trying to push it out, and that pressure balances the pull of gravity. But eventually this nuclear reactor will run out of fuel, and then what should happen? It has to, then there is nothing to stop gravity from making it collapse. Chandrasekhar found that there is something called the degeneracy pressure which can keep it stable for a while, but if the mass is really sufficiently big, then nothing can stop the inward pull of gravity. And then such a star would gravitationally collapse inside to form a black hole. And this conclusion was so bizarre that leading physicists, including Einstein, refused to believe it for decades. I mean, in fact, Eddington kind of ridiculed Chandrasekhar to an extent that I think one of the reasons why Chandrasekhar left Europe and moved to the United States was because he felt that, he had no future in Europe. Einstein himself wrote a wrong paper showing that this kind of event horizon, what he thought was a singularity, cannot occur in a theory of nature. And it turned out that that paper was wrong. And it took almost 50 years, even though there was kind of mountain of piling evidence. It took 50 years for the mainstream physicists to really accept that black holes do really exist. And then nowadays, basically every galaxy we believe has in the middle of our galaxy, there is a huge million solar mass black hole. And there are some 100 billion galaxies in the universe. So we expect that there are 100 billions of black holes in the universe. It's not anymore some kind of a peculiar property that follows from some peculiar solution of Einstein's equation. It is something very, very real. And Chandrasekhar had a very beautiful quote that he says that, because there is one very simple solution which is called the Kerr solution, the black hole solution. And he says that it's amazing that that simple equation describes all these astrophysical objects exactly, the space-time around this. And this is quite remarkable actually, because the gravitational field around, say, this table is very complicated. Because the table has, or around the Earth is very complicated. Because the Earth has mountains and it has valleys, so it's not exactly spherical. It has some quadrupole moment and so on, right? So it has, its gravitational field is not exactly spherical. But for a black hole, the black hole is really exactly spherical. The event horizon of a black hole is exactly spherical if it is not spinning. And if it is spinning, there is a slight modification. But once again, there is a very simple solution you can write down to Einstein's equation, and that exactly describes the black hole. This is truly a remarkable kind of an achievement of the human mind, you could say, that somebody just wrote down some equations, and that solution of that equations actually describes all these very bizarre objects that people are now beginning to discover experimentally. But it took 50 years to detect, to have anywhere convincing evidence for black holes, because most of the evidence was indirect from this X-ray emission, as I told you. But now the most dramatic evidence came in the most recently, from the LIGO experiment. And 2 years ago, this was detected in a laser interferometry lab. So basically you have like a laser going for some 4 kilometers and back. And if a gravitational wave passes, it gets jiggled a little bit. And that's how you detect that a gravitational wave has passed. And they found a gravitational wave that was created 1.2 billion years ago. So for those many years, that light was just, it was not light, the gravity wave, which at the speed of light, it was traveling towards us. And it just so happened that some people who sort of evolved from monkeys, just at this time had created a detector to put it there that they could detect it. And this is a simulation done by this LIGO collaboration, which I will run for you. So these are two black holes going around each other and merging into a big one. So all these little dots are stars, and the stars are kind of getting deformed by the gravitational field, and then it becomes one big black hole. And now suppose you start with one black hole of 30 solar mass and another black hole of 30 solar mass, and if the final black hole has only 50 solar masses, then by E is equal to mc square, the 10 solar mass energy is emitted in terms of gravitational waves. And it's so enormous that actually for a fraction of a second it dominates the entire radiation emitted by all the stars in the universe. So it's something very, very powerful event, because that's the kind of event that's the only way we can actually get gravitational waves sufficiently powerful that we can detect them. And you require extremely refined instruments, these laser interferometers, to detect them. But the combination of these two, amazingly, we have been able to. And this took 100 years. So this is you should now keep in mind the scale of experimental physics sometimes can be 50 years or 100 years, for detecting, especially when you're dealing with gravity. You don't get a verification of your theory immediately the next day. So by now I think most physicists, but I remember actually I was at Caltech when Kip Thorne and people were beginning to, were actually LIGO. I mean, nobody really took them, people thought this was really a long shot, when are they going to detect it? And mainstream astrophysics community also expressed a lot of skepticism. But it's remarkable that these people really drove this project, and now it's going to be a huge field of a new kind of astronomy, because now you can see the universe in a completely new spectrum using a completely different radiation. So it's as if it has been likened to similar to the discovery of a telescope by Galileo, that you could now see stars in a new, using a new form of radiation. So to summarize, we have the theory of relativity, and that's going to be the main, for black holes, that's sort of where the main things happen. But that's only one side of the story. The relativity describes nature at very long distances, all the way from the solar system to the universe itself. And it can describe all kinds of exotic objects like pulsars and black holes and so on. It's a very powerful theory, works extremely well in its own domain. It generalizes Newton's law of gravitation such that it's not instantaneous, but it travels at the speed of light. And it predicts gravity waves and black holes. But this is only one part of our story. The other part of our story is quantum theory. So quantum theory is sort of the other extreme, that it describes nature at very short distances. Once again, it has been enormously successful, perhaps even more successful than relativity, in describing atoms, molecules and physics of the atomic nucleus in terms of particles like electrons, quarks and photons. So it's a and everything that we use nowadays in our modern technology, from semiconductors to lasers, really require quantum theory. You need to understand quantum theory if you want to really design a semiconductor. So it is, whereas relativity has remained a bit more, except for the GPS. Nowadays actually the GPS that you use in your phone, now the accuracy has gone high enough that you need to take into account effects from general relativity. Now, one of the very important predictions of quantum theory that goes back to Dirac is that it predicts an antiparticle for every particle. So, for example, the antiparticle of an electron is called a positron. So, it has exactly the same mass but opposite charge. That's called an antiparticle. And that prediction will play an important role in the later part of the story. But despite the enormous success of these theories in their respective domains, there is a fundamental and very serious contradiction. When you try to marry them together, it just doesn't work. And the problem is roughly that we know that roughly we understand using Newton's law of gravity how the earth goes around the sun, right? To leading order is like Newton's law of gravitation. But you should be able to calculate some quantum corrections to it. And if you try to actually calculate them, and you expect them to be small because it's a correction, it's not the main effect, you actually find instead of something small, something infinite. And this is a very fundamental kind of a flaw, if you like, with the general theory of relativity or with quantum mechanics, we don't know which one. And these contradictions become even more glaring if you try to study the quantum properties of black holes. And in physics, whenever there are such contradictions, you don't despair. I mean, these are actually opportunities. I mean, because almost every progress in physics has come about by trying to resolve contradictions like this. For example, we saw Newton's law of gravitation was in contradiction with the fact that the speed of light is constant, is the upper limit. And to trying to overcome that led Einstein to develop his theory of general theory of relativity. In fact, so all over the history of physics, anytime there is a contradiction, it's actually an opportunity to try to find a bigger framework in which in some limit it looks like quantum mechanics, in some other limit it looks like general relativity, but there is some in-between domain where both effects are important, and then you have some framework to calculate them. And it's very important, I mean, okay, you could just say that, okay, I only care about semiconductors and lasers, I don't need to really worry about them. But it's a bit like, having on Mondays and Tuesdays, you read one book of nature and you draw one set of conclusions, and then on Wednesday, Thursday, Friday, you read some another book and you draw some totally different conclusions. This kind of thing we don't want to have in physics, right? We want to have, one big book of physics which is valid throughout the week, and not on different days we have different beliefs. So, and these contradictions become really glaring when you try to study the quantum properties of black hole. And that's why people like me and many physicists nowadays are interested in quantum black holes, because it's kind of a place where the contradiction becomes more severe, and that's therefore you can try to learn something about them. And one of the famous works, so basically the goal of one of the goals that is driving some of the research like me and other people is to find a consistent quantum theory of gravity that combines relativity and quantum theory, and physics of the black holes continues to inspire research and provide new clues about this theory to come. And I have to say that we are still quite far from the final theory. We are a bit like in the early days of quantum theory, which took some 50 years to really. I mean, people didn't come up with the quantum theory overnight. So, and one of the important consequences when you try to combine quantum theory with relativity was discovered by this famous work of Stephen Hawking, that black holes are really hot. They are not just black, but they are hot. What does it mean? That he discovered that because of quantum effects, black holes are not really black, but they are slowly emitting radiation, very much like a hot piece of coal or a hot piece of metal. And that is called Hawking radiation. And this is quite a remarkable connection between relativity and quantum theory. It requires both relativity, because it requires black holes, and it requires quantum theory, because it requires particle-antiparticles. So roughly an artist impression is something like that. This is a black hole. Okay, this is like a throat is like you're falling into the black hole. And this is your event horizon. And as I told you, in quantum theory, every particle has an antiparticle. And in fact, as we speak, the pairs of particles and antiparticles are constantly being produced and annihilated. We don't notice them. So near the black hole also there is a electron, positron. They live for a very, very fraction of a 10 to the minus, very, very short time. Milliseconds, like that. But every once in a while, one of these particles can fall inside. Once it falls inside, it cannot escape by the force of gravity. And the other guy can escape far away. This is the source of Hawking radiation. So this is a kind of a heuristic way of understanding how Hawking radiation happens. That there are virtual particle pairs, electron, positron, all over the place, even in this room. But near a black hole, what is special is that there is an event horizon. So once in a while, one of those pairs can fall inside, the other pair goes far away. Then it would look to you as though something is being emitted from the black hole. So even though black hole is really black, when you ignore quantum theory, when you include quantum theory, the black holes are actually hot. So let me take a pause since it's halfway time. Are there any questions? Feel free to ask questions, because I would want to make it completely interactive.
When you're saying a black hole is capable enough to absorb a huge body inside, how is it that one of the antiparticles is escape from that? We are talking about very minute particles.
See, it's not true that, for example, if you take a spaceship, you can keep on circling a black hole forever. It's not necessary that you always fall in. So only if you're headed exactly towards the black hole that you will fall in. Right? There are stars that are going around a black hole. There could be a black hole there is a black hole in our galaxy. We are not falling into that black hole. We're just going around that black hole. So depending on which way you come out, you see, it's not just going in or out. You can space-time around it. Yes. So a black hole is not an object, right? As we saw, black hole is event horizon. Black hole, a correct definition of a black hole is a space-time where there is this weird surface called the event horizon, which is a one-way surface. It's like a door of this room, You can only enter this lecture. If you get bored and you want to leave, you can't leave. It's like that. Right? So if you're inside a black hole and you go to a lecture inside a black hole, you're stuck there forever. So therefore there is no surface of the black hole. It's not like the surface of the sun. It's just space-time. And in fact, this event horizon is a very peculiar object. It's kind of a global, it depends on the global properties of space-time. So for example, we could very well be actually falling through an event horizon. There is locally, if you look in the size of the room, nothing strange could be happening for the black hole. It's only when you look at the whole space-time that you discover, actually the people who are falling are not going to come back. But that you don't discover. The person who is falling is merely falling through and will not find out until a million years later that, okay, they're going to get crushed. So, therefore, you're right that it's not a property of the black hole, it's a property of the space-time. But that space-time is called a black hole. I mean, black hole is not an object, black hole is a space-time.
Don't you think that we have understanding from a star which is not a black hole, the way black hole will be formed?
Yes, so we can form a black hole by collapsing a star. But once the black hole is formed, it forgets about how it was formed. Whether it was formed from throwing in chairs or tables or by something else. Then the space-time outside is completely determined by the mass of the black hole. And if it is spinning, the spin of the black hole. That's what is the remarkable property that Chandrasekhar talked about, that unlike this table, it completely forgets all the details, whether it is bending up or bending down, whether it is square or circular. Once it falls in, all the information about this table and chair is finished. You just get a exactly spherical black hole. And it's completely determined just by the mass of the black hole. So that's why it's a very universal solution of Einstein's equation. Yes? Yes? Sorry, I'm going backwards. Just a second, sorry. For some reason, I'm going backwards. Okay, sorry. Ask. That's a separate question. I mean, it's a very good question. He's asking that if the laws of physics require every matter to have antimatter, why do we see only matter sitting here? No? Why isn't there an image of anti-me somewhere? So that has to do with how to generate this matter-antimatter asymmetry. And at the moment, there is no fully understood. I mean, there are very good ideas using CP violation and out of thermal equilibrium. I mean, Sakharov had some condition. How to generate this? There are situations in the early universe which can create more matter over antimatter. But to my knowledge, I mean, the issue is not completely settled. How? But I mean, it's not settled, but I mean, it's not like it is something impossible to achieve. I mean, it's not that there is no completely satisfactory theory, but it's perfectly possible to have matter over antimatter because the universe was not in equilibrium to begin with. So a technical definition of the event horizon, it's a stationary null surface. Stationary null surface. Okay, let me explain. Stationary meaning what? That thing is stationary, right? I'm stationary and that is stationary. It's not moving with respect to me. Its position doesn't depend on time. So that we are always used. We are also used to null. Null means speed of light. If you take this is a null line. This laser, because it is moving at the speed of light. So as you're going forward in time, it is covering so much distance, right? It's going over there. It's not stationary. Event horizon is this peculiar geometric property that it is at the same time stationary as seen from the observer at infinity and null. So it's a stationary null surface, which is why it has all these very peculiar causal properties. Yes? Yeah, please. Yes. Yes. Correct. You are correct, and that was also the same question that was asked here. That most of the matter that we observe in galaxies is actually matter, and we don't see antimatter galaxies. And why that happened has to do with the history of the universe. And there are plausible models of how that can come about, but not yet completely, fully accepted theory. So PCT is always not violated, but CP, there is another symmetry CP which can be violated. So PCT can never be violated in a local quantum field theory. So that's it's a theorem. but CP can be violated.
How can you distinguish event horizon to singularity?
So as I told you, so Einstein actually, if I could be wrong on this, but my impression is that Einstein actually thought that the event horizon was the singularity, and he was completely wrong about that. One way to distinguish that is that there is some kind of a coordinate singularity, meaning if you just use weird coordinates, it would look to you that your space-time is singular. Okay, for example, if you use polar coordinates, in a plane, then what does the distance is like dr square plus r square d theta square. At r equal to 0, the polar coordinates are not well defined. So, but that's a coordinate singularity. You know that if you go to the Cartesian coordinates, there is no singularity. So event horizon is a place like that. There is no local singularity. There is nothing is diverging. It's not that the force of gravity is becoming infinite. As I said, we could be falling through an event horizon and you would never know. Because if you're a large enough black hole, the force of gravity is very weak actually, even at the event horizon. Whereas a singularity is really a singularity, and that it is inside this black hole. Inside means actually in the future, inside and in future. So that's the difference between a singularity and an event horizon. The singularity is a genuine singularity, meaning physics really fails there. And we don't know, I mean, one of the open questions is to understand what happens at the singularity. Similarly, the cosmological singularity, physics really fails there. Current theories of physics, we don't know. And string theory and quantum gravity is one of the motivations is to try to understand the physics of the singularity.
Might there be a difference between event horizon and singularity? Is there any physical any difference between these?
For example, if you are familiar with general relativity, if you calculate any curvature tensor here, it's finite, nothing blows up. Whereas at singularity, things blow up. Maybe I will take your question in the end. Okay, I will illustrate on a blackboard. Maybe that will be easier. Any other question?
Sorry, what was the question he asked?
What is the difference between a singularity and an event horizon?
What is the first one? What is the second thing?
It was the same question asked in a different way. Isn't it? Or was it? Yes. Okay. So that leads to a notion of quantum space-time or quantum gravity, that in atomic theory, we understand if something is hot for a metal, one of the great successes of 19th century physics and early was the discovery of the statistical mechanics, right? That you could explain thermodynamic properties from mechanics. What does it mean? That things like temperature, which is thermodynamic, you explain that in terms of motion of atoms, right? In this room, if you put a heater, the temperature goes up. But that also means that a typical molecule is moving much faster. So what is hotter is if the atoms are moving faster. Atoms vibrate faster if the metal is hotter, or the air molecules move faster if the room is hotter. So this was sort of led to the quantum theory of matter. One can ask a similar question: if the black hole has temperature, as Hawking has discovered, then there must be an explanation of that temperature in terms of some underlying constituents. How can you explain the temperature of a black hole? What are the atoms of space-time? Because it's like a hole in space. As I told you, it's not an object. Does it even make sense to ask this question? An answer to this question actually will lead us to string theory and ultimately to Ramanujan. I should probably hurry a bit. Let me see. So instead of temperature, actually it's more useful to talk about something called entropy. Now, how many of you here have, maybe raise your hands, how many of you haven't heard about entropy? Okay, you have not heard about entropy. Okay, everybody has heard about entropy, so I will just very quickly go through it, and I can be fast. It's actually a very subtle and profound concept in physics. One doesn't appreciate it when you study it in undergraduate physics. And it started, trying to develop good steam engines and so on, heat flows, to explain this fact, why does heat flow from a hot body to a cold body and not the other way around, right? Or why doesn't you can break an egg easily, but you cannot put an egg together easily? And how do we quantify this irreversibility that we see around us? That things can break more easily, but they don't come together so easily. Or temperature always flows in one direction. I mean, heat always flows in one direction. And this led to various engineers actually. Carnot was an engineer and made very important fundamental advances to physics. He defined this quantity called entropy such that the change in entropy is the amount of heat that you add divided by the temperature at which you add it. So for example, in this room, the room temperature is 300 degree Kelvin, and you put a heater, you can measure how much heat you're adding to the room, right? By looking at how the meter is running, the electric meter. And from that, you can calculate divided by the 300 degree Kelvin, that will give you the amount, the change in the entropy of the gas in this room. And then the second law of thermodynamics says that in an irreversible process, delta S is always greater than 0. And this is an intrinsic property of a given system and is a function of the energy. So like the gas in this room has entropy, which is a function of the temperature of this room or the energy contained in this room. And hot bodies have entropy. And now since hot bodies have entropy, a black hole should also have entropy. And this actually led to this discovery of the entropy of the black hole, not just the temperature of the black hole, but the entropy of the black hole. So how does one explain irreversibility? Maybe I will skip this since I don't have time. But one of the important points why this entropy, maybe I'll describe this. So entropy is actually useful for explaining the irreversibility because, now it's going forward. This is going backward. I don't understand how it works. I think I have to press here. Okay. See, if heat flows from a body at temperature T1 to a body at temperature T2, the net change in the entropy is absolute value of the heat, and the body which gives out heat minus the body which gets heat. And since delta S has to be always greater than 0, sorry, the other way around, you conclude that T1 has to be bigger than T2. Right? So the second law of thermodynamics explains why heat flows only in one direction. But there is an even more fundamental reason why second law of thermodynamics is important, and this is why it is one of the more profound concepts in physics, is that Boltzmann said that the entropy is related to the number of ways, different ways the system can be in the same energy. So if in this room, for example, all the molecules can be in many different ways, right? One molecule can be going that way, another can be going that way. Still the total temperature is 300 degrees. And you count all possible ways in which this gas molecules can be going around. You call that P of n, where n is the energy. Okay, I'm just using a notation which I'm going to use later. And then Boltzmann said that S of n is the logarithm of that P of n. So number of different ways one can partition the energy. You can divide the energy of the system in terms of 3 particles going that way and 2 particles going that way, or 3 particles going up and 1 particle going down, things like that, right? And this explains entropy. Why this is so fundamental is that because it gives an important connection between macroscopic thermodynamic quantity, which is the entropy, and a microscopic quantity about how the system can organize itself in many different ways, P of n. So this explains the irreversibility in terms of some kind of a statistical tendency, because if you shake a jigsaw puzzle, it is much more likely that it will break than if you take a broken jigsaw puzzle and if you shake it, it's highly unlikely that it will suddenly organize itself, right? Just because the number of broken states is many more, and whereas the number of states in which the jigsaw puzzle is properly made is just 1. So just statistically, there is a tendency towards disorder, and that explains the second law of thermodynamics. Now, this has turned out to be very important in black hole physics, because if black holes are hot, they must also have entropy. And in fact, Bekenstein and Hawking discovered a very beautiful and general formula for the entropy of a black hole, that it should be proportional to area divided by 4, where area is the area of this event horizon. It's a completely remarkable formula. So now we have a connection not only between relativity and quantum mechanics, but we have a connection between relativity, quantum mechanics, and thermodynamics. And therefore, by Boltzmann relation, it's a very good question to ask, What explains this entropy? Just like we could explain the entropy in this room by saying that, okay, the room is made up of molecules, they're moving this way, that way, I count the number of ways they can move around, I take the logarithm, that's the entropy. And it actually agrees with experiments. So if you put a heater and did a change of entropy and you did a calculation, the two things agree. So therefore, can we explain the entropy of a black hole in terms of counting of something? That's the question that leads us to string theory. So string theory is at the moment a theory, but it gives rise to general relativity and many quantum field theory in a very natural way. So many physicists believe that it's actually a theory that is on the right track as a quantum theory of gravity. And moreover, it overcomes some of the difficulties of quantum gravity that one encountered earlier. But it has to move in some 10 or 26 space-time dimensions. And the basic idea is that fundamental constituents are not really point-like electron. We think of them as point-like, but that if you look really with a bigger microscope, inside they're like a little bit of elementary string. And so the different elementary particles correspond to different musical notes produced by the elementary string. And since everything is made up of strings now, so this is a very nice unifying picture that all possible particles, gravitons, electrons, protons, everything is just a different way. It's like notes of a sitar string. One is sa, the other is re, and other is ga, and so on. So different notes of the string correspond to different particles. And therefore, even a black hole must be made up of strings or similar objects oscillating in many different ways. Moreover, as I told you, we live in a three-dimensional space: height, length, depth. Right? This room is three-dimensional. There is a height, length, and there is depth, and time. So there are, if you denote them as 1, 2, 3, and 0. So this is direction 1, direction 2, and direction 3. And then there is time. So there are 4 directions in space-time, dimensions. But string theory requires additional dimensions. For example, 4, 5, 6, 7, 8, 9. Or it can go up to 26 or 25 here. These extra dimensions, then the question becomes, why don't we not observe them? What does it mean that we have extra dimensions? But the idea is that these extra dimensions could be curled up into a small compact ball, and we will not see them. If the compact ball is really tiny, we will not see them in our daily life. But we will be able to see them using black holes, as I will explain. So this is the idea of compactification, that imagine an insect living on a wire. The wire is actually not just one dimensional, right? Wire has thickness. But the insect is so big that the insect does not notice that the wire has a thickness. So it can be that just like the wire is sort of rolled up in one direction and is long in another direction, it's kind of compact in these directions and long in another direction. That's the idea of that we imagine that can happen in our world. And then a class of black holes in string theory is described in terms of strings oscillating in many different ways. And so the problem of explaining the entropy of the black hole amounts to explaining how the total oscillation number has to be n, but the string could be oscillating this way, it could be oscillating that way, it could have a long oscillation on this or a very short oscillation. There are many different ways I can have an oscillating string with a total oscillation number n. And the problem becomes computing the partitions so that the number of oscillations is given by some integer n, and the number of ways the string can oscillate is given by what is known as the partition of the integer Pn. So this problem basically reduces to finding the partitions of an integer Pn. And moreover, because the string can oscillate in 24 transverse, so you have a string, but as I told you, you live in 26 dimensional space-time. So the string is one direction, then time, so this goes away. So there are 24 directions which are transverse to the string, and it can oscillate like that. Like, see here, the string can oscillate only in 2 directions, because it's stretching this way, it can oscillate this way or it can oscillate that way. So there are 24 different types of oscillations, and we have to do this counting problem. And this is what leads us to Ramanujan. So Ramanujan, this is the picture of Ramanujan. He is one of the all-time greats, like somebody in the class of Euler and Gauss, who made profound contributions to number theory. There is a very nice movie I will later on show a clip of that movie because it's kind of relevant to our discussion. The Man Who Knew Infinity. And he was a person with really very singular gifts and a remarkable intuition for numbers. And his very inspired ideas, sometimes he used to say that he got his inspiration from the goddess of Namagiri. Which it's a kind of a figurative way of talking about it. But it's really like very beautiful mathematics came to him almost from God. And this has kept mathematicians busy for decades. And he was interested in exactly in this problem of finding the partitions. These are called partitions with color. So he was actually interested in this problem of finding the partitions of an integer n. For example, suppose you want to partition an integer 3 using two different colors. Right? There are many ways you can write it. You can write it as green, 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 brown, 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 green, green, brown, like that, So the number of partitions in this case is 10, let's say. Okay, if I counted it correctly, it's 10. But now you imagine taking 24 different numbers. Sounds like a very, very simple problem, right? But it turns out to be a very, very interesting and important problem. And leads to all kinds of deep mathematics, which I will explain. So Ramanujan said, okay, it's actually a good idea to think of a partition function. So you should have 24 different colors. So let me write it as 1 plus q square plus q cube plus q dot 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 to the power 24. 1 plus q square plus q square, sorry, q to the 4, q to the 6. Sorry, I have made a mistake here, 24. In general, 1 plus q to the n, q to the 2n, like that. And now you expand it. For example, the number of ways you can get q cube here is here, this term will contribute, or you can take a product of these two, q and q square. So there are many different ways, and it turns out that using this partition function you can calculate. So Ramanujan's prescription was that just take this partition function, you can compute p of n by looking at the coefficient of q to the n in the expansion of the partition function. So this is a very simple, you can put it on a computer, right? You take this, multiply this so many times and just ask if you want n 100, you can calculate it. The problem though is that, and moreover, you can readily evaluate it using the geometric series. You remember the geometric series from your high school mathematics, right? 1 plus x square is 1 upon 1 minus x. So if you look at my partition function, it's going to look like there was a 1 upon q which I had added for some reason, but that's not the main point. But it's 1 minus q square, 1 minus q cube, 1 minus q to the 4, and so on. It's a very simple function. And now this function is an example of what is known as a modular form. And modular form, one way to think about it is that it's a very symmetric function. You are used to thinking of symmetric objects. Like a sphere is very symmetric. What does it mean by symmetric? That you do something to it, you rotate it, it comes back to itself. Relative to that, a hexagon is not so symmetric, but a circle is much more symmetric. Modular function, a form, is in some sense a very symmetric function. And one of its symmetry properties is that if you write this q as e to the minus 2 pi t and express q in terms of t, then z of t is basically related to z of 1 upon t. This is a very, very nice, very, very important symmetry. I will not be able to explain why, but you can sort of see that it relates the behavior of the function at very small t to the behavior of the function to very large t. And using this symmetry, Ramanujan was able to kind of calculate this, solve the problem of partitions in a kind of in a much more elegant and powerful way. So I will actually show you a movie where they talk about this. So this is a movie about Ramanujan. Sorry, what? Okay. And this person that is shown, this is McMahon. He was a kind of he was a major in Madras, and he was a bit of an arrogant, probably a slightly racist mathematician of that generation. So this movie is actually quite nice. I recommend it because it brings out all the kinds of difficulties that Ramanujan had to face. Bad food, cold weather, going from Tamil Nadu to there. There was war happening. His letters were not reaching his wife, so she was there was no communication. Then he got tuberculosis. So it is on this background that he created this very remarkable mathematics. So this is a scene in which Hardy, who was Ramanujan's mentor and a close collaborator, who took him to Cambridge, says that Ramanujan, you're on the breakthrough kind of, there is some breakthrough on partitions that you're going to make. But McMahon is the like a world authority on partitions, so why don't we go and talk to him? So this is like a 2-minute, I will quickly flash this. Sorry.
Fair on price. Just turn down.
Give me the,
Partitions. Can't be done, I'm telling you.
give me this. Is it good?
No, by hand, by slow and painful motion, you will be absolutely certain that whatever formula until
So basically here, McMahon gives him a challenge.
Now, how high do I have to go?
So he says, how many, I want to calculate a partition of an integer.
P of 200 should work.
So it's 200.
I really can do it.
Well, here we are, P of 200, the moment of truth. I was stationed in the Dresdens. Well, you first. What does your formula give you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
Okay, so he was actually exactly in this movie what is shown is finding the partitions of an integer as large as 200 using a single color. Huh? I'm asking about the color with 24 different colors, but very, very similar problem. And how did Ramanujan do it? He did it because he had this magic formula and he could just plug it in here, put n is equal to 200 and you get an answer pretty accurately. But he of course had a much more refined formula which allowed him to calculate even corrections. Now this brings us to the black hole story, because if the black hole is made up of this string and if the problem of finding n partitioning has been solved by Ramanujan, we just have to look up the formula and we take the logarithm of that, we get 4 pi square root of n. And remarkably, in this set of black holes and actually very broad class of black holes, people have found very similar calculations. That you calculate area upon 4. In this case actually it's not area upon, this example is, this side is a little bit harder to describe. But broadly speaking, basically you calculate the same quantity in very completely different ways. One is geometry. You find a solution, a black hole solution, there is an event horizon, you calculate the area of that event horizon, you divide it by 4, you get some answer. That answer depends on n, which is like roughly the energy or some quantity like that for the black hole, some charge actually in this case. And then you go around and think of the black hole as being made up of little bits of string and you calculate that quantity. Completely different calculation. And they agree. In exactly the same way that the entropy of the gas in this room, what Maxwell and Boltzmann did in 1860 and so on, was that they had this remarkable idea that you just think of ideal gas, this room is filled with little balls of molecules moving around. They used Maxwell-Boltzmann distribution, they calculated the entropy, and it agreed with experimentally observed entropy. So this is an analog of that statement. So I will now try to wrap up my talk, but Ramanujan, as I said, not only gave you this 4 pi square root of n, but he had a much more powerful result which is which is known as the Hardy-Ramanujan Rademacher formula, which can explain this log of Pn as an exactly convergent series, infinite series, and he was able to calculate all these coefficients. So when he went to meet McMahon, he can just go to arbitrary accuracy and calculate the number of partitions of an integer, no matter how big the integer is. Whereas McMahon would have to really sit down and calculate by hand. Right? We take an integer and then write it so many different ways. 1 plus 1 plus 1 plus 1. Imagine if you have 2000, then there are so many ways you can write. 1 plus 1 2000 times, or 2 plus 2000 times, like that, right? And that actually grows exponentially. Now, if I have another 5 minutes, let me bring you to some of the more recent topics which has been a sort of subject of my own research. So Ramanujan also had something called the Mach theta functions. Okay, so Mach theta functions, in his famous last letter to Hardy, so he died in 1920 quite young, he was not even 40, and he gave 17 examples of Mach theta functions, which he found very interesting. Okay, he just said that they are very interesting. They look like Mach modular forms. One of the examples is this, if you and I, mere mortals, look at it, it doesn't look very interesting. But Ramanujan had seen some pattern in this set of functions. And despite much work by many eminent mathematicians for 100 years, this problem was unsolved till almost 80 years. This problem was finally solved in 2002 by a student of Don Zagier, with whom I later collaborated, because Don Zagier is a number theorist. And we were just discussing this, and I was encountering some problem, and I asked him, and he said, okay, this problem has been solved by my former student, and there is a connection, therefore, of quantum black holes with Mach modular forms. And the connection is actually quite interesting. These Mach theta functions have found an unexpected application in study of quantum black holes in situations where one has both multi-centered and single-centered black holes. So I told you that you have a black hole, but in some situations what happens is that you have a black hole, but you also have other configurations which are multi-centered, which from far away they look like a black hole, the same black hole. So you have to count not just these black holes, but also these two black holes. And there can be 3-centered black holes and so on. And trying to solve that, do the counting of those states, counting of states for these kinds of in these situations, very naturally leads to Mach theta functions. So let me conclude. We are still quite far from having the final theory of quantum gravity. So I don't want to give you an impression that, in science, ultimately the proof has to be in experiment. So string theory has many things going right for it. It overcomes some of the very great difficulties of non-renormalizability of gravity and so on. It has led to some very deep insights through duality and holography, which I won't be able to explain. But many of them have originated from the study of physics of quantum black holes. And so even though the finding experimental evidence for this theoretical ideas has been hard, there is no question in the minds of people who work on it that clear progress is happening, and we are sort of, whatever is the final theory of quantum gravity, some of these ideas will surely play a role in it. It may not be exactly in the form that we envisage it now, but maybe it could be like quantum mechanics and early quantum mechanics, right? The two formulations were completely different, but there were some ideas which were eventually correct. So therefore it remains an exciting frontier for research in theoretical physics, and maybe there is some Ramanujan in this audience, who knows? So one of the younger people maybe will take it forward. I'll stop here.
Thank you. My question is related to the origin of black holes. One origin possibly, as you said, is, let's say, a star like the sun, after some time runs out of fuel, shrinks into a black hole. Is that the only possible origin of all black holes, or is there any other possibility?
People have speculated about primordial black holes. meaning black holes which could have been, because very far back in the history of the universe was very hot. It was filled with hot, dense gas, and there could be density fluctuations which could collapse to form a black hole. But I would say that most black holes which have been observed are most likely the ones which have been formed later by gravitational collapse. But primordial black holes is a theoretical possibility, but it's not very widely, I mean, but it's a possibility. It's a possibility.
And the one we have in the center of the Milky Way galaxy.
Yeah, that I think is formed by just, because once a black hole forms, then it just keeps eating up everything that's in the vicinity. So it just gets fatter and fatter. And that's how it's, if you are surrounded by some gas, and once there is a kind of it's a gravitational instability, is an instability. Once a black hole is formed, it becomes, just makes it worse. So it forms, gobbles up more and more and more matter. So that's the most natural way in which a black hole gets formed.
Other questions?
Sun, yeah. Yes, so sun is not going to form a black hole, but if you take a star slightly bigger than the sun, maybe 2 solar masses, and even if it so there is the Chandrasekhar limit because of which you cannot, the sun will become a white dwarf and will not become a black hole. But quite a large number of stars in the universe will end up in being a black holes.
We don't have a theory for supermassive black hole as of now, not by the stellar collapse. We don't know how they.
Yeah, these supermassive black holes were formed quite early in the universe. So, so there are now billions of solar masses. So the one in our galaxy is million solar mass. Supermassive black holes are billion solar mass of that order. But those are very early in the history of the universe. And because they are so far back, our understanding of those black holes is also relatively not at the same level.
So,
but I should just make a comment. For example, the black hole at the center of our galaxy, I was recently, 2-3 years ago, I was invited to this Kerr conference in the honor of this famous Kerr. There is a Kerr solution, Kerr. This is the solution that, so there was a Kerr conference, and where Kerr was felicitated. This was the 50 years of the Kerr solution. And I heard a talk, I mean, now there is an event horizon telescope. People are, and I think it was recently in the news, actually, I have not followed it. So people are really trying to look for the, you need a resolution, even though it's million solar mass. A solar mass black hole has a radius about 3 kilometers. So if you have million solar mass, it is 3 million kilometers. That's still very small on a cosmological scale, astrophysical scale, right? 3 million is, the distance between Earth and Sun is 150, how much is it? Yeah, something like that, right? So, so you need a very high resolution to really see that there is a black hole and there is nothing else. And people are now sort of combining radio telescopes from around the world to really develop the resolution so that they can sort of really have the resolution comparable to the event horizon of the black hole. So the black hole which is really close to us, we are likely to learn a lot about it in the near future. But some of these black holes are very far. But the evidence from LIGO was one of the most spectacular things, because there, 2 black holes are merging into each other. And that merger is described by Einstein's equations. You know, these are nonlinear, complicated second-order differential equations. But in principle, you can put them on a computer. And there is numerical general relativity, is a now highly developed field. And the kind of profile that you expect, of a signal that you expect, was precisely what was observed. So I think there is much, in some sense, that evidence is much more dramatic and much more convincing that it really is a black hole.
Sir, I heard that at the time of the Big Bang, there was pure energy, and once the universe started expanding, the energy condenses to matter, forming the fundamental particles. So my question is whether the pure energy, have any mass, or suddenly the concept of mass evolved when it the energy cool down to subatomic particles. Whether pure energy have any mass.
So if you by pure energy you mean particles like photons, right?
Yes.
Radiation, they don't have any mass.
So once they cool down, immediately they got the concept of
But they
mass.
can, yes. See, energy is conserved in these processes, and it can be, for example, two gamma rays can annihilate and form a electron positron, or two electron positron can annihilate. So these kinds of processes can happen all the time. So energy is conserved, but mass is not conserved in this process. So it is completely possible that pure radiation goes into pure matter.
Okay, sir. And two more questions, sir. Just you told that black holes can emit radiation in the form of Hawking radiation. So if we are giving enough time, will the black hole lose mass and
yes.
disappear?
We expect that to happen, but the rate of radiation is very slow for a big enough black hole.
Okay,
so
sir.
it is not going to be observed experimentally. It's unlikely.
Okay, sir.
The rate of radiation becomes very high as the black hole becomes small. The temperature is inversely proportional to the mass.
So it accelerates.
Yeah.
I think we should let other people ask questions as
So
well.
one last question, sir. And can we create a black hole in a lab, a small scale black hole, a nano black hole, something like that? I heard like that.
Yeah, but it's very unlikely. I mean, people have speculated about it, that if you bang with enough energy, but it's, yeah, in some models of physics of extra dimension, that possibility was considered.
Yeah. So you did this, you explained thermodynamics in terms of this counting of configurations. So, and you said for the black hole, you're counting some kind of atomic configuration. It was not clear to me what those atomic configurations are.
Okay. So the idea is the following, that suppose this is our this is our three-dimensional space, and you have a black hole here. But in string theory, there can be an extra dimension here, which is like a little circle everywhere. I mean, imagine there is an additional dimension here. At each point, there is an additional dimension. So here, there could be a string that is wrapping this extra dimension. So from far away, it would look to you like a local, just like a point-like object. But actually, if you go deep inside and if you probe it at sufficiently high energies, it would look to you that it has additional dimensions. There is a string wrapping there. And this string can then vibrate in many different ways. And those are the microstates of the black hole. I'm simplifying things a lot. I mean, actually, there are more complicated objects like D-branes and so on. What I tried to present was a kind of a very somewhat simplified version, which is slightly inaccurate, but I think it gets the idea across correctly.
Hello. Once the black hole allows something to radiate, it's not deserved for a black hole.
It's no longer a black hole.
Yeah, it must be called a compact mass object.
Yes.
That's all. Then how it is allowed something to go out, emit?
Yes. The special property about the black hole, I mean, that's correct. So the black hole is not really black, so you should change its name. But the thing is that
the definition of a black hole is it never allowed to anything to radiate.
To escape, exactly.
To escape.
But that is
the velocity of black hole is more than the c.
Yes.
So how it is called as black hole?
Okay. The point is that, as I told you, there is relativity and there is quantum theory, and they work well in each of their domain. If you completely ignore quantum theory, which you cannot really do because the world is quantum mechanical, if you completely ignore quantum theory and just think in relativity, then black hole is a well-defined concept. But what Hawking showed was that once you include quantum effects, there is a small correction to this picture. Now the temperature is very small. You see, the temperature for a solar mass black hole is so small that it is smaller than the 3 degree Kelvin cosmological background. So it's not that we are going to see the black hole becoming hot. But that's a theoretical possibility. And it raises all these theoretical thermodynamic questions. But it's only classically that you see that a black hole is black. Quantum mechanically, it's not really black.
Other questions?
Okay.
Sir, black holes are like super singular points, like space-time singularities. Am I right?
No. As I told you, there is nothing singular happening at the black hole, right? The horizon. What
No,
happens
not the horizon. I'm talking about the black hole in the
inside
future.
of the black
I'm
hole?
saying.
But
Like,
nobody, if you go inside, you will never come back to report what you find
okay.
out.
No, my question is, like, if there is a super singular point there, then we know the position of the super singular point. Then the quantum, how to say?
Fluctuation.
Yeah, the uncertainty principle. We
Yes.
know the position defined. So then, what happens to that?
So as I told you, this you might think. So let me write to you the black hole solution. Okay, those of you who know what a metric is, the metric of a Schwarzschild black hole is very simple. You see, if you have time, space, and it's something like that. I was avoiding to use equations because to keep the audience, but it's actually simpler to explain using an equation. Okay, so there is two sphere. There is a sphere at each point. R is the radius. So R is the radius away from the black hole. Then there is time, and then there is theta phi coordinates on the sphere, right? So this is what describes the gravitational field around the sun, for example, right? If you're standing far away from the sun, right, there is time, there is a radius from the sun, and then there are the angular coordinates. R is equal to 2m is called the event horizon. And R is equal to 0 is the singularity. And at R equal to 0, something really bad happens. Things sort of become infinite. At R is equal to 2m, something bad seems to happen, but it's like a coordinate singularity. Very similar to the singularity of suppose you had a polar coordinate metric into a plane. This metric is looks singular at R equal to 0, right? Because the distance is going to 0. Similarly here, at R is equal to 2m the distance, but we know very well, I can make a change of coordinates and write it as dx square plus dy square. And then there is no singularity at x is equal to y equal to 0. So the main point is that the event horizon, what Einstein thought was a singularity is actually was a coordinate singularity, but it actually corresponds to some weird causal properties. So to that extent, it is some kind of a singularity, but there is nothing is diverging. It's not that the physics breaks down there. Physics breaks down here. Einstein's equations break down quantum, everything breaks down here, R equal to 0. We don't know what it is. But R is equal to 0 is actually inside the black hole, and instead of looking like the singularity over there, so this is time, it's actually a singularity in the future. So it's actually a very strange thing, and I cannot explain it. I cannot do justice to it in a short answer.
Other questions?
So what is the difference between a photon sphere and an event horizon?
Photon
sphere, like I have read that the photon sphere is defined as the place, the maximum distance in which the photons can orbit the black hole without falling in. But that is not the definition of the event horizon.
I mean, you are imagining things going in a circle like that.
Yeah, like beyond that, if the photon enters, then it has to fall inside.
Yes.
But at that point, at that distance.
Yeah, so for the Schwarzschild solution, I don't quite know what you're talking about, but I think there is another point in this which is a bit further away here.
Yes.
It's not the same as the event horizon.
Yes, sir. It's not the same.
It's not the same, yeah. So there the causal structure is not changing. Causal structure it's not a stationary null surface.
Yes.
It is a special point, but it is not a null surface. See, what is funny about event horizon is that, null surface means on a spacetime diagram, it is moving at the speed of light.
Yeah.
So R is equal to 2m, actually even though it looks like it is over there, it's actually moving at the speed of light. Photon sphere any other radius is sort of like is a time-like trajectory. Whereas here it's a light-like trajectory.
Okay. Last couple of questions.
Sir, I just want to know, when the black holes merge, whether neutrinos are released?
Neutrinos.
And if so, when we are observing the sound by LIGO facility, why not neutrinos be observed like that? If at all they emit.
So in the case of two black hole merger, you only get gravitational radiation because the black hole is completely specified by just gravity. It doesn't have any other memory. But there was subsequent, this is called a multi-channel observation. There was subsequent observation in which a neutron star and a black hole merge.
Oh.
In that case, you can actually get a radio signal or some other signal. And that's actually very interesting new direction for this observational astronomy, because since you can observe the same event in two different channels, in radio and in gravitational wave, you can understand it much better.
Sir, one more question. The quantum gravity and supergravity, how are they different, or they are the other sides of the same sides of the
No,
other sides of point?
they are actually completely different. They are completely different. Quantum gravity means that you want to combine quantum theory with gravity, and gravity is described by relativity. Supergravity is when you want to combine a symmetry called supersymmetry with Einstein's theory of gravity. So it can be completely classical. A supergravity theory does not have to be quantum necessarily. Yes. So you can have a classical supergravity theory and a quantum supergravity theory, or you can have just a quantum gravity which is not super.
Okay.
So all these possibilities are there.
Thank you, sir.
My question is again related to the Hawking radiation that we discussed initially. While explaining that, you were saying that the radiation necessarily doesn't come from within the black hole, but it could be something which happens at the event horizon level. Yeah. So if that is true, then there is no case of even after billions of years of Hawking radiation, a black hole would continue to exist. Like it will not decay because the radiation per se doesn't originate from within the black hole.
It's actually, it's a funny property. You could say that it is actually originates inside, because the particle which falls inside, you see, as you know, the energy, the concept of energy in general relativity is a bit, right, you can have redshift. So the particle which falls inside has negative energy in some sense, compared, as viewed from the observer's point of view at infinity. So therefore, it looks like a negative energy particle has fallen in, which brings down the energy. So it's consistent with energy conservation. See, otherwise it would be inconsistent with energy conservation, right? That you would get a lot of radiation out and the mass would still be there. So the mass goes down in exactly the same amount as the energy that you extract from it. And it's consistent because of this peculiarity about how you define energy.
So which means that the radiation does come from within.
You could therefore view it as, since a negative energy particle you can think of as but traveling backward in time. You could view it like that, but okay. But the physics is really happening near the horizon.
Okay, I think we can wrap up. Let's thank Atish again for a very nice talk.